kind of problem that we're looking to solve here is what we call the connectivity problem. So tokens are good, everybody likes tokens, but tokens will only form, in our opinion, somewhere to 10 to 20% of all smart contract functionality. Because if you look at, why do we like smart contracts? We like smart contracts because they can handle the complexity of mimicking actual financial agreements. And if you look at actual financial agreements that rely on digital state in securities, insurance, trade finance, any of these industries, they commonly require inputs. And that's where they gain their efficiency, right? They gain their efficiency from having a data point, such as a market price, or a GPS, or IoT, or any number of data points, resolve them, right? Whether they're a complete contract that can be resolved completely by that data point, or whether they're an incomplete contract that's only partially resolved. The large efficiency gains you see from kind of digital financial agreements is based on the fact that they are automatically triggered by data feeds as objective proof of performance, right? So that's a quality that we think blockchain-based digital agreements, smart contracts, should also have. But they don't have that quality natively, right? So this is not the most well-known thing, except if you've gone pretty far in the development process. But basically, every smart contract network out there, if it's actually run on decentralized infrastructure that's tamper-proof, it cannot talk to external resources, right? So this is due to the nature by which we arrive at consensus around blockchain transactions. It's not very clear which of the parties in the consensus mechanisms now would do this, right? Like you don't have miners putting in external data feeds, partly because many of them would have different values. You would have lack of consensus, you would have various security concerns, and so the simple hard fact, you should absolutely look into it, but for the sake of our presentation, we're going to assume that smart contract networks now and in the kind of foreseeable future are not able to talk to external APIs or data feeds or any kind of external resource that isn't already on the network, right? So our goal is to solve this problem. That's what our company and our body of work is pretty much entirely focused on. Right? So how we seek to solve this problem is something called blockchain middleware. So blockchain middleware basically allows you to ingest various types of formats, whatever they might be. They might be JSON, they might be XML, they might be a proprietary format, relatively proprietary, like Swift messages, FPML, whatever format your data comes in and you'd like to ingest, blockchain middleware, or good blockchain middleware, would allow you to ingest the data in that format, and then it'll turn it into something that can be given to the contract, right? So the goal is to get the data to the contract with as little headache for the developer as possible, right? Because the developer, when people build things like Uber or any of these other apps that we like, they don't build all the surrounding infrastructure, right? Like Uber didn't make the GPS network that the US government launched and then opened up. And then Uber didn't make a ton of libraries that Uber is built on, right? And likewise, smart contract developers shouldn't have to make all this middleware stuff. They should just have a whole set of tools that if you want this off-chain resource, you get it. If you want that off-chain payments mechanism, you can get it. So that's what good blockchain middleware, in our opinion, does. Is it solves that problem of getting that resource to you easily. And it should do that on all the dimensions on which you need an external resource for your smart contract, right? So right now, the most pressing external resource is data, right? Because you need to trigger the contract. If you're doing something beyond tokens, if it's a security, smart contract security, it commonly needs price, data feeds, market reference data, some kind of market data. If it's an insurance contract, it needs Internet of Things data. If it's a trade finance contract, it needs GPS data, customs, border protection API, confirmation, any number of other data feeds. So what we're initially focusing on is how do we get data in from other systems, right? Because that's what people they need that today to build their thing today. The second thing people need today is they need payment mechanisms, right? They need a payment mechanism that end users want to accept. Right? It's not really our place as people who make products for users to tell them, you really have to take Bitcoin for this to work. Or you really need to take whatever thing that I think you should get paid in. The best products don't tell users, you need to do this. The best products just go, you're a user, tell me where you want to get paid, and you get paid there, right? Like, that sounds a lot better to us. So smart contracts should be able to do that. You should be able to say, I'm a user of this type of smart contract product. I want to get paid here in this format. Here I am. Here's my info. And the smart contract should just do that, right? At least that's what we believe. And then there's a lot of cross-chain stuff this can do. But cross-chain is a bit of a ways out, so we're not really going to focus on cross-chain, because cross-chain only becomes important, in my opinion, when you have data and payments in other chains that you care about. Until then, cross-chain is fantastic, and we should all work on cross-chain, and we'll move towards cross-chain stuff, but it's kind of like, when the world gets there, that's when we should get there, right? But there's use cases where you need super cross-chain stuff, and we can support those, but that's just not our focus is the data and the payments right now. Now, I think I made relatively clear why this is important, but basically, we want smart contracts that are competitive with existing digital agreements, right? If you have basically, a security that uses digital state, or an insurance contract that uses digital state, or a trade finance contract that uses digital state, right? Those contracts, I'm checking the box of like, can I trigger the contract with the data feed? They check that box. Can I pay the user out in the 5 currencies that all the different users want to receive? They check that box, right? If we want smart contracts to be competitive with those products, we need to give them that capability, right? Otherwise, the smart contract would be a fantastic thing in the middle. There'll be this awesome technology in the middle that we're all excited about, but it won't really do much other than its native token-based functionality, right? That's kind of the hurdle we're trying to help people clear. And that's like what is exciting for us, is when people go and they build something cool because we were able to help them get the resource they wanted. But the key dimension here is also, as Grant mentioned, it's security, right? So what we think is good right now is we all believe that the smart contract is this secure shared record that can process digital agreement logic, basically, right? But as we try to make these contracts that need inputs and need outputs, we kind of expand our vision to the end-to-end setup, right? And we ask the user to do the same, right? We ask them, well, you need to trust not just the thing in the middle now, you need to trust the kind of stuff on the perimeter of it, right? The thing that gives it the data, the thing that triggers it, the way by which it pays you, and this end-to-end setup needs to retain a relatively high level of security and tamper-proofness in order for the user to look at that product and to go, oh, okay, I get it has the super secure thing in the middle, but the end-to-end setup is also pretty secure. And so I am comfortable with not putting $100 million in a traditional financial product in a centralized system. I'm comfortable with putting $100 million in a smart contract in a decentralized system, right? Like that's the outcome, in our opinion, we kind of would seek to achieve even as a community, regardless of whatever we're doing. So our approach to this is really pretty simple. We have this blockchain middleware. We've been building it for over 3.5, close to something like 4 years now. We've been successfully giving it to companies like Swift. They've been using it internally. We've had a number of data providers. Other people set up their own oracles as a way to sell their core service to smart contracts. And what we're basically doing now is we're making it so that you can use this blockchain middleware in a decentralized fashion, right? So what that really means is that if you wanted to have 5 oracles or 10 oracles, you could choose to do that, right? You could say, I don't want just the one data feed going through a centralized service that then triggers my contract. You could say, I want some level of, like at the smart contract level, I get massive decentralized infrastructure and consensus, right? And it's really distributed and it's huge. But what we're saying is you might want to have a layer of some amount of decentralization between this super decentralized thing and the completely centralized kind of data feed that's triggering it, right? And that's where the decentralized Oracle network actually provides. For the people that want some level of assurance on the basis of decentralization and multiple independent nodes, they can now have that assurance based on, I selected these 5 oracles with high quality reputation, and they executed these actions for me, and I have proof that they executed the actions correctly, so that I know that in a decentralized manner, I have been able to ingest data. And so I trust the data on the basis of decentralization, less decentralization in the smart contract in the middle, but perhaps enough decentralization to make you comfortable that the data input is sufficiently decentralized to kind of raise that end-to-end security perception that we talked about, right? So that's kind of what a decentralized Oracle network, in our view of things, should achieve for the end user, right? Is that perception, or that reality from a security perspective, whatever you want to call it. So as you can see from this graphic, we seek to achieve this for all the external resources, and the way we go about achieving it is we allow data providers, payments providers, and basically any developer who knows an API to generate a chain link that represents that API or that data feed or that payments mechanism on chain, right? So something like 3 years ago or 3.5 years ago, when we started out doing this, what you had to do was, as a smart contract developer, you had to go and you had to figure out the API, and then you had to build the blockchain middleware, and then you had to hope it all works. What you could do, like basically now, and starting maybe a year or two ago, was you would figure out the API, you would go to a blockchain middleware centralized service, you would give them the API, we have such a service, and in 11 minutes you would turn that API and its outputs into a contract that other contracts could talk to, right? Kind of the world we should be going to is the world where every off-chain resource that a contract would want to interact with has a contract on-chain that represents that off-chain resource. So that you as a developer don't need to go and figure out like Bloomberg's or Thomson Reuters or data provider X or payments processor Y. You don't need to figure out their weird API. You don't need to figure out an interface that isn't related to the smart contract, right? You just have the smart contract, send a transaction on-chain to another contract that is the right interface, right? Like that's the interface that you want your contract to interface with for this off-chain resource, right? Does that make sense so far? Okay, great. So let's look at some level of detail. We'll have a white paper coming out sometime soon, and that'll have much more detail. But we're going to look at some level of detail of how this actually functions, right? So for data inputs, the first thing that you would have a data provider, whoever it is, Bloomberg or any other data provider. They would set up a chain link, which is basically a piece of blockchain middleware wrapped around their interface, wrapped around the API interface, right? And that chain link now has a contract that represents the functionality of that data provider on-chain, right? So just like you have different API requests you can make, now you have different on-chain transactions that you can make to get the same result, right? Like just map API request number 1 to on-chain transaction number 1. API request number 2 to on-chain transaction number 2. And that's it. That's basically what the blockchain middleware does. It does a lot of security and formatting in the middle, but that's kind of the goal, so that you show up to a documentation page that isn't API documentation, it is smart contract interface relevant documentation, right? Just like makes sense, right? I don't want to figure out things I don't need. I just want to talk to a contract that'll give me what I need, and I just want to pay it once for the one thing I need, and I just want it to happen quickly, and I want it to happen in this secure smart contract environment, right? So that's what this contract here represents. The next step in this process is the user decides, okay, I want to deal with this on-chain contract that represents data provider X. I know what I want from this on-chain contract. I know I want to do transaction number 4 and 5 because I need this type of data in this way, and so on and so on. The user generates the requesting contract, and then in order to talk with the data provider on-chain, they generate a set of SLA terms. Right? So now they have a standard way to generate basically a request, an on-chain request that a Oracle contract can understand, that a ChainLink contract will understand. And this is basically definition, right? This is, I want this data type in this format at this time period for this long for this price. It's a service level agreement. It's very simple. Right? This is a standard we have for creating how a contract should ask an Oracle to give it something. Basically a service level agreement that's on-chain. This service level agreement contract, which receives the terms, then sees, okay, you want to talk to this specific data provider chain. Okay, sure. It goes to that contract that represents the data provider, and it says, here's the price they're giving you, here's what they want, here's when they want it, here's the frequency, here's all these details. and then the data provider's contract, presumably with an automated policy, will just go, yes, I accept that. That's within my parameters. It returns a kind of, yes, I accept it. And that's it. Kind of the service level agreement is now kind of basically signed off on by the provider. The requester has given it to them. And they are now basically in a contractual on-chain arrangement that's proven on-chain, right? That you're going to do this, this, and this, and you agreed, and that's on-chain, and people know that. And so people looking at the requesting contract can now be assured, right? They can see, yes, you have contracted with this specific data provider who has this type of reputation, with this level of quality, and therefore now I can trust that your contract will execute correctly because you have a very specific, very well kind of vetted or high reputation source kicking off the key parts of our mutual contract. Right? So you want the other parties in the contract to be able to understand what it is that's going to be kicking off their $100 million smart contract security. You want to make that simple, and you want them to be able to look at the reputation of who's doing that. And you can do that with multiple people, right? So this is where the decentralized part comes in. It's that you can do this with as many oracles as you'd like, as many oracles as you'd like to pay for, basically as many as there are, and you basically send SLA terms, and those get distributed to the very specific providers that you said, I want to deal with these providers. And so you can have a contract with 5 oracles, all querying 5 separate data sources, or if all 5 oracles query one data source, whatever configuration of data sources and kind of oracles that you would like. Also not our place to tell you that. Our place is kind of to create the system that you use to get the type of decentralization you'd like to have, whether it's on the level of the intermediary or if it's on the level of the data provider. Now, what happens next is that the requesting contracts begin receiving on-chain data, and the off-chain data begins to flow into the ChainLink, gets converted into on-chain data, and the requesting contract can do any number of operations between it and the contract that represents the data feed. Right? It can ask for more, it can ask for less, whatever's defined in the SLA. Now, the service level agreement at this time is basically monitoring all this behavior. It's basically looking at, it's getting pinged by the contracts that are fulfilling their obligations. It's seeing that the requesting contract is getting that. And it's basically performing a kind of ongoing on-chain auditing role where it's tracking what is going on, right? You agreed to this service level agreement to do these types of data inputs at this frequency, with this format. It checks as much of that as it can check. And that generates on-chain reputation history for the different providers, right? Which can be relied upon because you can actually see, okay, these guys did 1,000 Oracle contracts in the past week, and they all fulfilled them successfully, and they all did it to these specific contracts that seem like legitimate individual contracts, and so I know this data provider can successfully execute on my contract as well, right? So the SLA is basically the contract that monitors what's been agreed to and generates a certain amount of on-chain reputation that other parties can in the future rely on when selecting who their provider will be. Right? Now, this initial version of it, this is the initial version. This is what we internally call the direct contracting version. This is where the user shows up and says, they do a bunch of research, they look at the interface for searching the kind of ChainLink network, and they choose very specifically, I want the first best Oracle and data category X, and I don't want the second one, but I want the third, and I want the fifth, right? And so they've chosen very specific providers, and they've put it into SLA manually, and they've gone ahead and done this whole process, and the contract has been agreed to, and it has begun, and it's being monitored by SLA. The more complex and more efficient version of this that basically requires sufficient market demand, right? So it's something we're working on, and it's something we plan to at some point put out there, but it requires sufficient market demand, is the ability for those SLA terms to be given to what we call a market contract. So the market contract is basically a contract that can do dynamic bidding with multiple data providers, right? So once you have a sufficient group of data providers that are, let's say they're rated AAA, right? You have 50 AAA data providers for the federal funds interest rate, which is a very common thing for many smart contracts. Well, maybe not yet, but it will. It's a very common metric for many financial instruments. And at that point, once you have such a large amount of data providers, you want an efficient system, right? You want an efficient system by which people can do bid and ask around, I am asking you for this type of data, what price can you give me? What price can the other AAA rated data provider give me? What price can, what can we do on a market basis in real time, right? And that's what the market contract does, is it very quickly kind of does basically order matching around a specific resource. And so in reality, you might end up at a point where there's enough reputation and there's enough clarity about the quality of a ChainLink node and a ChainLink provider, data provider, that you're just fine with saying in your SLA, I want a AAA provider with 99% uptime, and I want them to be able to do X, Y, and Z, and this frequency for this period, for this price, or this range of prices, right? And the market contract will then do bid and ask matching around that to create efficiency. This is a later version of this approach. Now, this version is also monitored by the SLA, and so basically that model is retained in this version of the world. The matching happens, but the reputation still remains in the way we described. Okay, so there's payment output ChainLinks. How am I doing on time? How much time left? All right, I have a few minutes.
Half an hour.
Okay, great. There's like some pressing questions, so I'll answer them, and I'll try to answer them quickly, and then we'll move on if it takes a little too long, if you guys don't mind. Yes, you seem to have.
All right, yeah. So I'm a little surprised. Thank you for your talk, but I'm
not done yet, so let's...
I know, I understand. So you said reputation 5 or many times. It implies that the content of the supplier contract is opaque, that you're picking the contract based on reputation, and that you can't examine. Is that what?
No, you can examine.
You can examine the code in the contract that you're subscribing to.
The code in the you can examine that the SLA as it was defined has been fulfilled by the contract.
That's what I'm asking the code in the contract.
Let's wait. Sorry, let's wait for it afterwards.
You're saying no.
Yeah, we'll have questions.
I'm not saying no. The off-chain computation piece and how you prove that is later in the presentation. Perhaps we'll just get to that part of that, and then we will do questions if that's okay, if that's all right with everyone. But there is an answer for that. So for payment outputs, so we've arrived at the place where now we have data inputs going into some kind of smart contract security like a bond, right? It's getting an interest rate, for example. It then uses that interest rate to calculate how much it should pay people, right? It says, I know what the rate is from the market, I know what I need to pay now, I need to pay it. In this situation, the smart contract security sends an on-chain transaction to a contract that represents a payments processor, right? It can represent a bank, payments processor that has a banking relationship, a payment network like PayPal. It doesn't matter. The point is that the goal here is that there's an on-chain transaction to generate an off-chain payment in another system. In this example, it's a bank. The bank uses ChainLink on the back end for ingesting commands from smart contracts, right? It has an on-chain contract that represents, I'm the bank X ChainLink. Here are the commands for payment that you can send me. And those payment commands are then sent to it, and then it executes them based on whatever parameters those commands give it, and if it's allowed to execute those. And then that means that now you can send an on-chain transaction for payment. The on-chain transaction for payment is turned into the payments messaging, whatever kind of system or standard or message that is used by that network, and that then converts into something that can pay to all the user accounts on that network, right? So it can, in the case of Swift, it can convert into over 11,000 banks in pretty much all the currencies of the planet, like USD, Euro, Yuan, all these things, right? So this is kind of the approach to payments. It's very similar to data, except now the contract is making an output. It's executing that output in an off-chain system, and the off-chain system is then commonly responding back to the contract to tell it payment complete, which in our experience of building these things for various production level use cases is when you actually have the contract completed. Believe it or not, most financial contracts complete when payment happens. So if you want to use off-chain payments, you're going to want the off-chain payment system to tell your contract they were paid. So that's another kind of, there's a forwards and a backwards roll in terms of the contract actually being completed by the response from a payment network. Just saying that's a very common kind of design pattern we've seen. Now, this is where we get into dimensions of how do we make certain Oracle operators secure and trustworthy, right? What you have in this scenario, for example, is let's say Standard & Poor's isn't running a ChainLink. Let's say there's a third-party developer who has a reseller agreement with Standard & Poor's, and they want to resell Standard & Poor's data because they think that's a great idea, and smart contracts would want to buy that data. They can charge a premium because they understand oracles and ChainLinks, and they can get the high-quality ChainLink up and running and sell high-quality data and get a big profit from it. Right? Let's say that's a scenario that exists. If that scenario exists, then you want to be assured that the node operator, that's basically relaying the data from the data provider, is trustworthy. And then for payments, you want to be assured that things like your credentials, your payment credentials, aren't being compromised if you need to provide them when you want to execute a payment. Right? So these things start to get into questions about how do I know that the Oracle is tamper-proof, right? We know the contract is tamper-proof, but how do we give people some level of assurance that the contract is tamper-proof and the middleware is tamper-proof, and then eventually the actual origin is tamper-proof, and eventually the payments output is tamper-proof, right? Like we want tamper-proofness throughout the entire chain of events, and this is kind of the beginning of it, right? You need to give a way to get inputs. You got it like 6 times, yeah. Okay, so the way we approach this is where things like town crier come into play. So town crier is an exciting approach developed by the folks at Cornell Tech, and something we've been working on with them, and something that we launched together with them this past summer. And it uses something called trusted hardware. So the way trusted hardware works is it basically creates what's called an enclave to execute code that has to be inaccessible to the environment where it's executed, right? So you will have an enclave that is surrounded by all kinds of other systems, but the enclave itself will not be something that the developer running that setup can access, right? So if you give the enclave specific code to run, the assurance that trusted hardware is supposed to give you is that the code it will run is the code it was given, right? And that the only thing that the developer running the trusted hardware setup can do is he can turn it off, which becomes immediately apparent, which affects his reputation as a provider of whatever service he's providing, which is very detectable, and it's not likely that person's going to have a very good reputation for doing anything for anyone. Right? So this is kind of the promise of trusted hardware, that it's a secure piece of the environment in which code is run, and we're talking about putting very specific Oracle-related and blockchain middleware-related code in this environment to create this tamper-proof trust, right? To create the trust that, yes, I'm a developer who's reselling access to a data feed, but I'm giving you access to this data feed in a way that I can't tamper with, right? I can't see what you're trying to do. I can't see exactly what you're requesting. I can't see your credentials, and this is what we want to keep private and tamper-proof, right? There's different views of this approach and whether it works and whether it doesn't. We think it's an approach that has promise, and we're kind of trying to move it forward, and we're basically moving forward and doing our best to make the town crier approach a better, more successful approach. So the way the town crier approach works, which by the way is developed by really smart folks. One of the lead authors on the paper is Ari Jules. He used to be the chief scientist at RSA. Very smart guy. We have the highest opinion of the people that put out this body of work. So I suggest you guys, if you don't think we're at a certain level, you should at the very least take a very good look at this. Now, the way it works is really quite simple. There's a user contract. There's an on-chain. Once again, there's an on-chain representation of the off-chain enclave, and the off-chain enclave receives the transactions or sees the transactions that the on-chain contract receives. And then the off-chain enclave processes those transactions. It processes like what those on-chain transactions told it to do. So it's pretty much very similar to the model I just showed you. except it's based on an enclave, right? There's a contract that represents the resource. The resource, in this case, is an enclave, which can execute certain specific functions, like get this data feed or do that computation. Right? And then the enclave reaches out to the data feed and retrieves the data that you need and gives it back to the contract, and that contract gives it to the user. So basically, it's an anonymous setup with what we've shown you prior. Now, yes, now we can look at your question. Yes. So what happens with something like SGX is you could send things on-chain, right? But that might become costly, or perhaps you don't want to send all your commands on-chain, right? Perhaps you want to send some of your commands off-chain because they're very large, or because they're, you want them to remain super private or something like that, right? In this case, what you would do is you would do a side-loaded query. You would send an off-chain query into the enclave. The enclave would receive that query, and it would issue a query ID, right? So it issues a query ID. It then generates a payment and a schedule that it gives the contract. So the on-chain contract says, okay, now I have this payment and schedule for executing this. The query ID is generated, and in answer to your question, what can happen is that a third party that is also part of the contract can at any time ask the enclave, perhaps by also signing with their key in order to get it, or in order to be able to decrypt the response. But they can ask the enclave, here's the query ID for the kind of Oracle operation related to my contract. Please give me what it says. Please tell me kind of what is going on inside the enclave. And the enclave can return to the person what it's doing in a way that the person is assured that that wasn't tampered with. Right? That the developer running the enclave didn't get in there, and that whatever the enclave said it's running at the time when the enclave is asked is what it's running. And so this creates a measure of audit for the other parties in the contract to be able to see that, yes, indeed, the trusted hardware setup that I'm putting my trust in is something that I can at least ask at any time. And if you're like a very antsy person, you can ask it every minute or every hour or however often you want to ask it, whatever you'd like to do. So this is one of the kind of approaches that we're looking at implementing sometime in the future around this process. And right, the next thing. Well, actually, before we go to the other cool thing, does that answer your?
It's helpful, and I'm starting to understand what you're saying. Thank you.
Okay, great. Glad to hear it. So. The next step, I guess, in the process here of understanding what we're trying to achieve is what exactly are we giving the enclave, or what are we giving an Oracle, or what are we asking an Oracle to do, right? And this comes back to the SLA or any number of examples like that. And we, from a usability perspective, think it's pretty easy to make it so that even if you want to do off-chain computation, right, you can write that off-chain computation in Solidity, right? So what you can do is you can write the contract in Solidity, and then if you want to write the off-chain computation, you can also write that in Solidity. And you can write Solidity around retrieving specific data feeds, right? I mean, Solidity is a good language, and a lot of people know it already in smart contract world. We could make a domain-specific language, and there's all kinds of approaches to that. But the reality is, from a usability perspective, it would be easier if, when you evaluate a smart contract, you read through the contract code, and then you read through basically the Oracle instruction code. And it would be a bit easier if you could read both of them in the same language, right? Especially if the developers that are going to be writing these things know Solidity, which I'm guessing that based on the fact that we're all here is what we're assuming. So that's that's an additional approach of what you would be putting into this off-chain computation environment. In this case, what's happening is we're basically asking for price data. We're asking for the enclave to decrypt credentials in order to get the price data. And when the enclave decrypts the credentials, it does it once again in a way that the person running that enclave, whether it's us or somebody else, cannot see your credentials, right? So this is an example of the code that would do that. And this is a simple example of that data then being computed and asked to be reported on chain. So this is an example of a very simple off-chain computation that generates an on-chain output based on the data that was acquired here through decrypting the credentials and then giving the data to this very simple calculation, right? Just as that simple example. Now, the next thing that we kind of realized with a lot of this work, and another direction that we're actively working in and actively putting forward, is basically the ability for the chain links to also do a certain amount of computation, right? So a chain link will be able to acquire the data feeds that it needs, and then it'll also be able to do computations that you would not be able to do on a smart contract network, or perhaps for privacy reasons, you might not want to, right? So a simple example is, something like a Monte Carlo simulation, where you don't want that simulation or the parameters of that simulation to be public, but you want that simulation done in an environment where the data comes in, and perhaps you want assurance that whatever the simulation was, it was done in an environment that is tamper-proof, because the other parties in the transaction still need that assurance, right? They can't have you get the data, do the off-chain computation, and then have you put in the data because you're a party in the contract, right? So a measure of off-chain computation is an extremely useful feature in our opinion, and it makes complete sense that you would pair it with the place where you ingest data, right? Because most off-chain computations, in our opinion, will require data, right? Or they'll possibly require to do a computation before you do a payments output, right? So it's just a very natural fit for us in that basically we expect a lot of off-chain computation around data inputs is the gist of it, right? So the other great feature of off-chain computation is that you can do private key control for smart contracts. So now you can have a smart contract that's running in this secure, trusted environment, which can control a private key and can act on that private key depending on the inputs it receives either from data or from other contracts. There's another interesting feature. We don't exactly have time to go into nuances of that use case, but that's possible, and that's something that we're pretty excited. We think that's going to be a very common use. The kind of other thing that we also think will be very common when you look at chain links that are able to ingest data and then are able to do computations around that data is the ability for kind of very well tested libraries around kind of critical operations to be run in the same environment as the off-chain computation, right? So what this means is you would have something like the EVM running in a trusted hardware environment, and then let's say you need randomness, right? You need some randomness generated so that your contract can now do something like a lottery. Let's say you have a lottery contract, or whatever contract where you need some randomness, which is a surprisingly large amount. Now, what we're basically saying is that there's entire bodies of work and there's kind of native libraries that generate randomness. And it doesn't make sense to us that you should reach out to an API to get randomness, right? There are very secure, very well-tested libraries for core operations, such as the generation of randomness. And what you can actually do is you can have the off-chain computation that defines what should be done off-chain in relation to the contract. But you can also have some of these native libraries running in the same trusted hardware environment, so that the off-chain computation doesn't even really need to reach out outside of the enclave to a data feed or some other local resource. It can kind of operate based on the inputs it gets within the enclave. And this is really just a move to make it so that the reuse of very well tested, very secure libraries for things like random number generation get a good amount of use. Right? So this is, random number generation is one, there's a bunch of others, but I think this is going to be a very, very common use case because a lot of these applications do need randomness. So it's very simple. It returns a specified callback to the specific function running in the off-chain computation, as you saw before, written in Solidity, more or less for ease of use and ability for anybody who queries the enclave to get back some code that they can read in kind of without having to crack open a book about code, basically. So, yeah, so those are the benefits. Just restating them, the privacy and the control of private keys, we think is pretty cool. You can, if there's a part of your contract, for example, that you don't want on a public chain, but you need it, you could theoretically contract with 5 Oracle providers, 5 ChainLink providers, and run that part of the contract in that kind of decentralized Oracle network. And then you would supposedly trust what that decentralized Oracle network returns, and you would essentially, effectively, you would have a part of your smart contract run privately in this secure setup. And the other part of it would be run publicly. Or at least, this is I would say, an incremental solution until you have something like encrypted on-chain contracts that can still be processed. And, that's a different approach to this, but that's farther away, and we think this is substantially closer, and something that, my ideas about what's useful are my ideas, but I think it's going to be useful. So, yeah, that's the gist of our approach. We're going to have a white paper out sometime soon with substantially more detail about how we're approaching these problems. We're excited to hear your feedback on that paper when it comes out. You can sign up on our site, smartcontract.com, and you'll be notified at some point that it's out. In the meantime, we're working very hard on this, and I guess that's it for me. So I guess we can switch to questions. Yes.
So I'm wondering, with the external data source, how does it handle backwards compatibility, like if that API endpoint had to change? And then I guess the same thing with like the ChainLink, as far as more like long-term things. If you say had a contract for data for like a month, that might be great, but then what if you needed something to be reliable for a year, or 5 years, or 10 years? How would it handle that? I mean, every time if that external data point changed, and then that would probably break that ChainLink, so you need like a new one to be compatible with that, and then spread that out to any contract that was using that?
Right, so there's two dimensions to this. This relates to how a requesting contract deals with the ChainLink contract, right? So in that vein, there's two approaches, right? The first approach is the direct contracting approach. And in the direct contracting approach, what you're saying is, you as a ChainLink node operator are going to maintain this ChainLink and its functionality for this period of time, right? And you're making that promise. And so if there's some kind of change somewhere, perhaps you handle that. Or perhaps you can't handle that, and perhaps that is reflected either in your reputation, or people decide that certain data providers commonly change all their data feeds, and so they might not want to, they might like the node operator, but they might not like that data provider, because they make it impossible for node operators to maintain their commitments, right? So that's in the direct contracting approach. In the market contract approach, the way this would be resolved is that the requesting contract would start once again dynamically bidding. There would be a dimension on which you could say, I know, like this requires a sufficiently large amount of, let's say AAA providers of your type of requested data. And then presumably if you have a sufficiently large kind of market of these providers, then it may not, and there's so much kind of reputational and data about them that the likelihood of there being any real difference between them is small. Then you can have a dynamic where, okay, one of them went out, or like you can even do it on a request by request basis if you really wanted to. And that's where the market contract really comes in. That's a better approach, but that approach requires, as I said, you have to have sufficiently large amount of AAA providers, or AA, or whatever level of provider you want to contract with. And so it doesn't just depend on technology, it depends on a sufficiently large group of people being able to participate in that contract. Does that make sense?
Right, yeah. And then I guess I'm also curious, with the secure enclave, wouldn't that require specialized hardware for each instance of the whatever
yes.
trying to execute?
Yeah, that's a bit of the holdup. So that's why this approach isn't really ubiquitous. This is cutting edge in terms of that hardware is not in Amazon, it's not in Azure, it's not in any of these places yet, right? And so the kind of assumption we're making is that this approach will have a measure of security, or even if not this approach, a trusted hardware approach, generally speaking. That's kind of the larger assumption. And then the smaller assumption is Intel SGX is a well-reviewed, kind of relatively seemingly well-made piece of trusted hardware. And it'll also assume, another small assumption would be, we're assuming that it will also become available enough that ChainLink, that if you're a ChainLink operator and you know you can get paid more if you run an SGX-enabled ChainLink, that when you go to Amazon, you have an SGX option to run your Docker image in, your ChainLink Docker image or something, right? So that's a hiccup, but it's one that is getting figured out as far as the people who provide trusted hardware. I think it'll happen because if trusted hardware actually functions, there will be sufficient economic demand for it, that there will be sufficient incentive for the trusted hardware company to provide it. There will be sufficient economic kind of revenue and capital there to buy it. Is my assumption. It seems very natural to me. So the only risk in my opinion is really, not the only, the larger risk in my opinion is that trusted hardware isn't secure. But that is, that's a very debatable thing. You can go to all kinds of conferences and talk about it all day, but it's not a fact you'll get an answer. Is that I see you.
Could you repeat the question?
Yes, repeat the question. Yeah. I never do that. Thank you.
Perfect.
Yes.
Okay, I was wondering, I know there are some projects out there where different data providers are staking coins with different game theoretic kind of mechanisms. If someone else they're disagreeing on stuff, to keep them honest. I won't go into the details of those things. So I was wondering, like in your example where you have these, what you're calling these AAA data providers, who is determining that they're AAA? Is this a centralized entity sort of maintaining that reputation record about them, or what's, that's like, seems like a missing piece in your explanation.
It is a missing piece in my explanation here, because we don't exactly have sufficient time. It is in the white paper that's coming out. What I can tell you, kind of in a very general sense, is that there are basic metrics which a user can evaluate about an Oracle's reputation. And then whether you combine those metrics into something like a AAA rating is a matter of how you programmatically, like an algorithmic basis, weigh those ratings, right? And then how do you generate an algorithmic programmatic way of combining those reputation ratings into AAA?
What are the metrics? Like, what's an example of a metric?
For example, if you've been contracted to fulfill a request, did you fulfill the request? How quickly do you respond to new requests, right? All kinds of, it's in the white paper.
Are there metrics about the accuracy of the data?
Metrics on the accuracy, well, yes, there's a dispute mechanism, and look, the reality is we can talk offline about this. It's a deeper question, and there's a breakout, like bullet point by bullet point, of the initial reputation metrics. And our assumption is quite simply that that's a question we don't fully know the answer to yet, of what reputation metrics are sufficiently predictive. And so we suggest a few initial ones, but in reality, people will creatively come up with much better reputation metrics than I can make right now, just standing here thinking about it. And so it's in the white paper, the initial ones, and we're glad to chat about it, but I don't think I'll fully answer your question if I stood here. I didn't repeat the question.
No, it's okay.
Sorry, I told you I got bad at that. I don't know. I guess this person.
So I wanted to know about offline human anomalies. How is that handled? For example, like the fat finger bug, where somebody accidentally enters some number and it throws the whole exchange off, and it throws off the numbers on the time.
Don't have fat fingers.
Where in the system would that type of anomaly be detected, or 9/11 happens and the market freezes?
I understand your question. My first answer is, generally speaking, these things is, stay awake, don't drink too much caffeine, get some sleep, don't have fat fingers. Second answer is, you have multi-signature schemes among contract participants and among important people in the system, where if you had an error scenario, you can have a multi-signature scheme that allows people to stop something or resolve something. That's really a question, that's a very contract-specific question, right? That's just kind of how do you write the contract that is ingesting data.
So that would happen on-chain? That would not be at the data provider level?
Yeah, the data provider's ability to provide accurate data is the responsibility of the data provider, right? If the data provider doesn't provide accurate data, there's nothing much, but the data provider provides it now to financial instruments, and they have legally binding service level agreements to provide it. And so we're assuming that all the data providers won't just one day wake up with fat fingers. The resolution of the data provider made a mistake that's the data provider's business, right?
Right, but I mean, it would be on the exchange where the mistake would occur. So if the data providers were all pulling from the same exchange, they'd all pull the same numbers. I mean, unless they did post-processing on the exchange numbers.
Oh, you mean if somebody put in a price that they want to pay for the data?
No, well, I mean, on the exchange, I've worked on option exchanges, and, somebody will put in have some computer program on there that causes, bullshit to happen, and the whole exchange goes haywire. I mean, all the data providers are going to just output the same job.
Oh, it's going to be very difficult to update the market contract. We have a section in our white paper about contract upgradability and how you upgrade something like the market rate contract, and that has a relatively technical overview. So I'm glad to chat about it after, but the reality is that the white paper will answer that question better. I guess this person.
Yeah,
Take the question.
this is somewhat related. So often financial institutions will have a data repository for Bloomberg information they pull in, so they can scrub it, make sure that if there is downtime, you have your own source to pull. So does the ChainLink provide that? So if your trusted data source goes down, that you basically can pull the last number that was available, until there's an update, so you don't get a null result.
Okay, it's probably the most difficult part of this for me, but I'm going to give it a shot.
Okay.
If a bank has a data repository that they rely on in data failure scenarios from the origin, can the ChainLink pull from the data repository?
Or there's a similar feature included in ChainLink, or is there not a kind of storage or look-back facility?
Right, so can I look at the data repository instead of the data feed? Can I do automatic switching, if the data feed returns an error, can I have a fallback written into the ChainLink, right?
Right.
Yes. That would be an off-chain computation, right? So that would be an off-chain computation where you define error scenarios, and then you define alternative sources. And that's very easy to do, right? Even in the code that I showed you, you would say, okay, source number 1, ask this one, if error or response time X, then switch to source number 2. Likewise, source number 3, 4, 5, whatever it might be, right? And then you would show that off-chain computation to the counterparty that you're in the contract with, and they would approve it. Then one of you would put it into the enclave. It would begin to run and feed the contract between you two. But then if at any point one of you wanted to validate what was happening in the enclave, you could ask, and it would return that off-chain computation with those error scenarios. Does that make sense? Yeah, okay, great.
So in the ChainLink, do you have when you're running off-chain computations, do you have the same features that you have in a normal smart contract? Is it immutable? Is there auditability?
It's a different set of trust assumptions, right? When you have the smart contract, this trust assumption is, okay, we have a decentralized network of node operators, they're all executing the same computations, there's cryptographic proof around those computations being executed. The trust assumption here is that trusted hardware is secure, and that trusted hardware can't be tampered with by the operator other than having the entire setup turned off. So whether you get the same exact guarantees, you don't get the same guarantees, right? You can get the same guarantees if you have an Oracle network, right? So if you have an Oracle network, if you have a smart contract network of 5 node operators, you have an Oracle network of 5 Oracle operators, then I guess you would have very similar guarantees, right? It's different. If you just have one Oracle running the trusted hardware, and then it's feeding into a network of 8,000 smart contract nodes that execute all the transactions, you're trusting trusted hardware at that point. Which, yeah, that's the difference. Does that make sense?
Yeah.
Okay. Yep.
How will you handle man-in-the-middle attacks where you have fed fake API data from one of your nodes?
Right. So this is where all kinds of schemes like TLS come in, and basically there's TLS handshakes between the data provider and the enclave, right? And there's even TLS handshakes between the enclave and internal resources. So it depends on kind of the existing certificate authority scheme for TSL and SSL, those types of things. Yep.
This solution introduces actually complexity.
Sorry, I can't hear you.
This solution with the enclave is actually introducing the complexity, operational complexity. The provider doesn't need to have the hardware. That's not necessarily straightforward. What was the trade-off? Why did you choose this solution? Were there other options, and why? Why did you choose this?
Okay, so the question is, trusted hardware seems to create complexity. Why did you choose trusted hardware other than other approaches?
Right.
I mean, the reality is we need to create some assurance that the ChainLink operator is executing the data request or the off-chain computation, right? There's ways to do that where you have a consensus mechanism around multiple Oracle operators, and there's ways to do that where you have trusted hardware. Those are the seemingly two approaches that exist. The reality is that we are doing both, right? So the reality is both approaches have their merits, and different people, like I don't know exactly how it's going to shake out. Like trusted hardware could be fantastic. Decentralized consensus without trusted hardware could be what people think is good enough. These are interesting questions. Deeply interested in these questions. But the reality is that the better approach is to make a system that's flexible enough that if you wanted decentralized consensus without paying the premium of trusted hardware, and that's what you believe, then you looked at the consensus algorithm of the Oracle network, and you decided that's sufficient for me, relative to some kind of cost or some expense that I save on, then okay, you can do that. If you, for whatever reason, don't feel that way, right, like you have a contract of more value, and you believe in trusted hardware, and you feel that a decentralized Oracle network with trusted hardware in the operators as well has additional value that you're willing to pay for, you should be able to have that, right? The reality is, if I had a crystal ball, I would choose one and go with one, but I don't know. And so we're doing both. I personally think trusted hardware, if it works, if it delivers on the security guarantees it says it delivers on, is a very interesting thing that can be useful. But whether it delivers on those security guarantees is a different question, which kind of only time will tell. But there's definitely very smart people working on it. So it's not something that I think should be dismissed out of hand. I don't know if that answers your question, but that's at least the perspective we have.
When the code is executed in the EVM is the enclave virtual machine, is that what that is? You have EVM on your last slide?
Yeah, so the EVM, the Ethereum virtual machine is running in the, let's just assume that's the case.
And is that code coming from the blockchain? Can you inspect that code, or is it by nature private, that code?
So if you do a side-loaded query into the enclave, that code will be private, right? If you send an on-chain transaction to the kind of contract that communicates with the enclave, then it'll be on-chain. You have both options. Well, once again, like our goal here is really quite simply to build a flexible system, right? Like there's if you look at this graphic, what you see is it's not my place to tell you to send payments with Chase or Citi or like anybody else. It's not my place to tell you to use this or that data provider. It's not my place to do decentralized Oracle networks that rely on consensus or trusted hardware, or whether you want to sideload your private smart contract code or send it on chain encrypted. Like our place is to generate the kind of body of work that can allow you to do all that stuff without having to figure it out, which in our opinion will accelerate what people can build, right? The way we're viewing it is that the reason a lot of cool things that could be built aren't being built right now is there aren't sufficient tools, right? There aren't sufficient ways to combine resources like people are used to doing in web development, right? They're used to combining libraries for specific inputs into their application. And the way we view this is we're basically building we're providing very specific building blocks. And in fact, we're not even providing them. We're allowing other people to decide, I'm a developer, I know an API, I know a data feed, I work at a payments processor. I have a way for us to make more money by giving smart contracts our capabilities, right? That's kind of so the goal is I don't know, I think I answered your question, but the general design principle, this is just a general design principle we're taking on is, our goal is to create kind of a decentralized Oracle network that has this flexibility. So that if you show up to a ChainLink and you say, I need this type of data, I need it to be computed this way, I need it to be output that way, and I need part of it to be private, I need part of it to be public, you can have all that. Right? That's kind of the design principle we have on that. We're good? Yeah? Or one more? No? All right.
All right, thanks guys. Can we give Sergey a round of applause? We have one quick announcement here.
Thanks, Greg. Hey guys, my name is Alex, and our team is working on a virtual reality Ethereum interface. We're looking for a technical writer who will help us proofread the white paper, maybe contribute a little bit to the technical sanity of what we got there, but it's all pretty much there. If you might be interested, we got cash, we got coins, we got equity. So if you're capable of producing a coherent English text, please come talk to me. Thank you.
Thanks, Alex. Also, let's give a quick shout out. Anshul and Sinchan are here from Proffer. They'll be presenting on September 10th, so please come and make that meetup, and I'll be announcing that soon on meetup.com, and they'll be presenting here at Digital Garage. And you can find them at Proffer, PROFFER.network, I think it is. Cool. Yeah, so once again, please round of applause for Sergey. Yeah, feel free to mingle with each other. We'll probably be wrapping up here in 20 minutes or so, 30 minutes, so we'll probably be putting chairs away and such. So yeah, thanks for coming. Have a good night.